Hello, we had discussed in the last two lectures how non-dimensionalization can be done for not just simple beams, but for the whole compliant mechanism. Today we will look at two examples to illustrate how we can use non-dimensional maps to design compliant mechanisms, or rather dimension I would say, that is topology we already have, something that from a database, which as I said in our lab we have about 80 to 100 of these compliant mechanism topologies. You can take any one of them, whatever size they may be, whatever material it might be made of. We can use that and then see if it can be used for some other application, whether it is micro or macro does not really matter, because what we have are non-dimensional maps. So, let us look at that. First let us recall what a kinetoelastostatic map is. So, we take any quantity, okay, let me dip the pen in some ink. We draw this map where we have eta, which is f s square by E b d. To recall, S is slenderness ratio, which is L by d. By the way, all these are average values, we just do not put them after some time. Okay, for different S values we have a quantity, it could be, so far we discussed displacement, let us say u out divided by L bar, that is not dimensionalized. So, we plot these things. So, it may be like that for one S, another S, another S and so forth, that is S1, S2, S3 and so forth. So, that is the kinetoelastostatic map. So, what it means is that if I have a mechanism, we can calculate eta value once we know forces, its slenderness ratio, Young's modulus, breadth and depth B and D. We will know S, let us say it is S2. Quickly we can find out what the non-dimensional displacement is. Since we know L bar, we can get the non-dimensional real displacement, not non-dimensional. Once you get this quantity that is non-dimensional, multiply by L bar, you get the displacement. How does one construct these KES maps, kinetoelastostatic maps? For that, in order to plot any one of these curves, let us say I have u out divided by L bar and then eta. I need to take any mechanism, whatever dimensions it may have, whatever material it is made of, does not matter. We take whatever we have on hand and do a finite element analysis. We have to do a nonlinear finite element analysis. Material is still linear, but geometrically nonlinear one, and we can draw, we can basically get many points, and if you take them close enough, you will get something like a curve, smooth curve, that will be for one S value, let us call it S1. That S usually we start from 10, because below 10, as we already discussed, it does not obey the beam theory on which this non-dimensional analysis is based on. So, we take 10 and then increase the value, do another finite element analysis and do it for 20 and then maybe 50, because 30 will be too close, and if you start doing, you will see even with 100, it does not, after a while even if you do 200 it will come very close. So, whatever more than 200 it does not really make sense, because it will become too slender. So, if I were to do for 10, 20, 50, 100, 200, I just need to do 5 finite element analysis. It may look like a lot of work, but it is actually only 5 nonlinear finite element analysis is all you need to do for a given suspension, that is all for this non-dimensional displacement that you want. Okay. So, it is just that we need to recompute the values in terms of eta and then this non-dimensionalized E out by L bar, which is not a lot of work, simple computation. So, constructing KES maps is really easy, it is not a lot of grudge work, it is just few analysis. Once you do it, you do not need to go back to finite element analysis, because let us say you have not done 30. So, you know where 20 and 50 are, you can actually intelligently interpolate back of the envelope calculations, you can easily do and find out what might be for this eta. If 30 are not done, you can say what that is, right. So, it is as easy as that. Okay. The first thing we have to do is, once a compliant mechanism is there, here we have a DACM, meaning this is displacement amplifying compliant mechanism, displacement amplifying compliant mechanism, what we call DACM for short. It is acronym abbreviation. In this case, segments, this is first we have the nodes 1, 2, 3 and 4 and so forth, and we also have this is segment 1, segment 2 and so forth. So, let us say this information is given to us. We have in a database a lot of compliant mechanisms, each of them, this is the node number and then x coordinate, y coordinate. What size it is does not matter. The size of this is given here. If you see, the maximum here is 0.8 here and this is 0.35. Okay. This is 0.8 millimeters by 0.35 millimeters, like a mesoscale mechanism, micro mechanism, if you were to make this. But what you need may be bigger than this, smaller than this, does not matter. It is just the size of the mechanism that is in the database. Using this, you can draw the kinetoelastostatic map. And for doing that, you also would need to know, once your coordinates, of course, you can calculate lengths of all the things and segments connecting which vertices or nodes. You need to know in plane width, you need to know out of plane thickness. This is something to note. This is the depth of the beam and this is the breadth of the beam. I use depth and breadth to indicate that this is D, this is B. So, that second moment of area for rectangular cross section is B d cube by 12. How do you decide this? The depth is the dimension in the plane of deformation. So, if I have a compliant mechanism, let me just show the in plane width here. This is going to deform in this plane when you apply the force here. So, that becomes the depth. So, in plane width is the depth of the beam and out of plane dimension, which is the breadth here, which is out of plane thickness. So, thickness is actually breadth here, B. So, when you have this data, you can draw the kinetoelastostatic map. So, in this particular thing, let us talk about how to design a micronewton force sensor. That is a force sensor that can resolve up to 1 millionth of a Newton, 1 micronewton. So, that is actually made in our group a couple of years ago, where it looks like this. What it has is a digital camera. This is a holder, this is the digital camera. So, the digital camera looks at a compliant mechanism, which is here. We will see a bigger view of that. It is not that small also, it is something like a mesoscale one, but made with PDMS, a very flexible material, and that will have a input here and that will cause output of a point amplified, which the camera looks at it, and then based on what camera measures as the output, we can estimate what this force is. So, that is the principle of this micronewton force sensor. So, the packaging it up, this is the holder and where the camera comes, this is the mechanism, this is the probe holder where the mechanism will be located, and you can put the whole thing, and it is more like a cartridge. You can put that, if it breaks you can put another one. It does not break because we make sure that when we design that it is strong enough. So, what is important here is the compliant mean that is inside this force sensor. There is nothing else. You can dip in water, you can put whatever fields, it does not really matter, and you can actually use this to measure forces that are applied on the cells or other biological things where the environment may not be suitable for other types of sensors. They may be very expensive, but here the expensive part is a digital camera, which also you can get for 5,000, 6,000 rupees these days, and they are certainly cheaper than some of the mobile phones, the smartphones you have, and after that it is just the compliant mechanism, our DACM. That is, you apply input force, little line you can see, it amplifies the displacement over there, that is the output. So, we need to design such a sensitive one which has effective stiffness of 2.6 Newton per meter. The device, if you see, this is 28 millimeters. So, it is a centimeter size device, 3 centimeters by 2 centimeters, but its stiffness is 2.6 Newton per meter, very low, or 2.6 micronewtons per micron. 2.6 micronewtons per micron. Apply 2.6 micronewtons, it will move by 1 micron over here, and over here it may actually move a little bit more because it is a DACM, and we can measure that use the camera, and that is how we get our micronewton force sensor. So, how do we design? The first thing is we have to get this L, or rather L bar. We have all these segments, we have length of this, length of that, length of this, you take the average. In this particular case, that L average for the one that is in the database is 0.6382 millimeters. You do not need so many decimal places, but since we are there, we have put. In fact, we are designing something very sensitive. So, micron and submicron also matters here, that is the L bar. And once you have L bar, you can choose a S value. We have, once you have L bar, slenderness ratio, which is L by D or L bar by D bar or S bar. So, most of the time in microfabrication, the in plane width is decided by the lithography limit. That in a particular process you can make it 3 microns, 1 micron, 5 microns, whatever your capability is. In this case, we chose 5 microns conservatively. So, you can actually get that slenderness ratio S here by taking that L bar you have divided by D. After you do that, you draw the curve, that is kinetoelastic map, and then what you want U out by L bar, U out is taken as 0.002 millimeters, and that is 2 microns. Why do you want 2 microns? The idea is when you apply, let us say 10 nanonewtons here or 10 micronewtons here, whatever is the force, you want displacement. The displacement here we want it to be at least 2 microns, because the smallest force that you want to resolve should lead to a displacement that measurable by the digital microscope here or camera. That. So, there we thought that if you have 2 microns, that microscope is able to measure. So, we have taken the U out L, then we get U out by L, non-dimensional number, and that is the y coordinate here, 0.003097 or 0.0031, and corresponding x here is the eta value, which is very close to 1, that is 0.002. Once you have eta, then you can find the in plane width that we wanted. Should be the D that we had assumed, but breadth, which is the out of plane thickness here, can be obtained because now we measured eta to be 0.002064, does not matter so many decimal places, but 0.002, and F is, in this case we have taken 10 nanonewtons, okay, 10 nanonewtons. S is 127 because we assumed D bar to be 5 microns, which is here, right. This is D, that is 5 microns. E we have taken 4 gigapascals. In fact, I forgot to mention here in the database over here for this mechanism, E was 4000 pascals. That is just something that was put in database, it does not really matter. Whatever it is, what we want is a non-dimensional map that we now draw. So, in the non-dimensional, what Young's modulus you take there does not matter, as long as displacement everything you have taken the consistent units. So, we have all of this. Now, we get B to be 4 microns, meaning thickness is 4 microns. If it is 4 micron thickness, sometimes could be too thin, in which case there will be problems of mechanism deforming out of plane, we may have to increase, and that may change this. That is exactly what we had done in another work. Santosh Bhargav and Nikhil, 2 students, had done this work for designing these mechanisms, not for micronewton force sensor that I talked about, but actually to measure the stiffness of cancer cells, breast cancer cells, the cell line Michigan Cancer Foundation 7 cells. So, we want to measure the bulk stiffness as if you hold a cell in your between your fingers and then see how stiff it is. Okay. For that, what they had done was they had taken a compliant mechanism, in which case we are calling composite compliant mechanism, meaning that there is a compliant mechanism inside a compliant mechanism. This particular big mechanism is, if apply input force here, these two jaws you hardly see the gap between them, but there is a gap there, it will just come together. When it comes together they touch, and that is when if there is in between, so this is another compliant mechanism which is blown up here. Okay, that is a mechanism inside another mechanism, then a composite compliant mechanism. Here is where the cell is, cell was red circle, now became blue when you do this, and here is where we have a DACM on the right side and the DACM on the left side. We have two displacement amplifying compliant mechanisms in such a way that this probe, if I put a cell here, the red one, when the force is applied over here, that is force applied on the big mechanism, small one here moves, and then this force applied by the cell or experienced by the cell would cause this output to move, and this is where we would want to measure using microscope. Usually any microscope you take will have a field of view. Now our field of view should be this big, so that we can see both DACMs and the cell that we are grasping. That was the constraint here. So, based on that, first looking at KES map for this mechanism. So, it will be like this, we had looked at it in an earlier presentation also. Eta is up to 0.6 we have drawn, and for S equal to 16.4, 32 and 82, and it has a maximum, all those features are there, but our interest here is a particular set of specifications, that is we want to be able to do this in a way that the mechanism, both mechanisms and the cell fit in a 2 millimeter diameter circle, that is what I had just drawn, that is this circle, okay, 2 millimeters. Based on that we can get roughly the L bar for this mechanism, okay. From that specification L bar for this is 0.7 mm, that is for a mechanism in the database we can get the average length of all the segments and scale up for what we need, the 2 micron thing that we want. Each mechanism gets 1 millimeters, 2 millimeters, 1 millimeter. So, L bar average thing becomes 0.7. And in plane width, which is the depth of the beam here, that is we are taking 5 microns based on the process. Then we get S or S bar to be L bar by D bar, which comes to 77.2, and we also now once you have this we can actually draw that. So, 77.2 we can draw this, and then we want U out by L bar. U out here we want it to be I think maybe 1 micron or 2 microns. I think in this case let us say 2 microns we take, and L bar we have taken this to be 0.3858 millimeters, 10 power minus 3. If you do, that comes to 0.0013. So, that is what is the y coordinate, something here there, and then corresponding eta we get very close to 0, that is what it is, 0.00085. Once you have that eta, okay, it went too fast. Yeah. So, once you have eta, you can actually calculate the B by F, because eta is F S square by EBD. We have taken B here, F here. If we do this, B by F comes to something like 346.5 here. Eta comes from that. S anyway we have already. E in this particular case is taken to be again I think 4 gigapascals, again SU8 material. So, E is 4 into 10 power 9 and D we had taken as 5 microns. If we do that, B by F turns out to be this value, and if I take F to be let us say 10 nanonewtons, that is I want to be able to measure 10 nanonewtons, so that I get a U out of 2 microns. If I do that, I get B to be 3.5 microns, and this will be the thickness here, because the breadth in this particular case it is a in plane compliant mechanism. That would be, I think this is going too fast, okay, that is 3.5 microns. On the other hand, if you think 3.5 microns thickness is too small because the mechanism will go out of plane, then this will be an issue. So, we want to increase it. Let us say I increase it to 15 microns, just so that out of plane stiffness is reasonable. Then if you recalculate this B by F, and F will come to 42 nanonewtons. So, if you want to have 15 microns as your thickness, then minimum force that you can resolve become 42 nanonewtons and not 10 nanonewtons that one intends. So, this kind of calculation will be very quickly done, because it is all in here in the kinetoelastostatic maps. Now, let us look at how it was designed. So, you can see this is the 0.7 we had taken. Overall size of this is 1.7 millimeters, they are all in millimeters, and this happens to be a small part of a bigger compliant mechanism. The whole thing can be made and immersed in liquid to handle biological cells. So, you can design whatever size mechanism you have using this technique, you can adapt it to the smaller one, decide the size of the thing. Similar thing we have done for cement tester mechanism, that is much bigger, much more force. We can actually estimate what should be the size, or manufacturing limits are there, we can say what is in plane width, thickness and so forth. This was the SU8 prototype that was done. Again you have the big mechanism where the force is applied over here, and this moves, and this is the blown up view of that, where you can see this length here is 500 microns. So, that is half a millimeter, and this actually shows this cancer cell, okay, actually grabbed here. You can see all the cells here, all immersed, and that is where this goes. You see DACM, yeah. So, this is the where output displacement will be, this is the output, and that is what camera will, in this case microscope will see and then estimate the force. Now, let us look at another thing, which are bistable arches. They are highly nonlinear because they are bistable, and for that also we can draw this kinetoelastostatic maps. So, in this particular case let us look at an animation. So, how this arch works, we are applying force here, it would go there, that is one stable state, another stable state, and this arch shape can be many types. It can be just a sine curve. In this particular case we call it a tin lid curve, because we have a tin lid here, which is a lid that can go bistable. It is a shell, and I can place it on this, and I cannot do this now because I cannot when I place it, but it is a nice feature on the sides which we can press on the sides and it would go, and then lid will be tight again. So, you saw the tin lid where we could switch it between two stable states. One was just up and down motion that we just saw, the other was sideward motion. So, the bistable arch that I showed in the previous slides, let us look at that again. So, here you see two pin joints, there is a pin joint here, there is a pin joint there. So, there is a pin joint here, there is a pin joint there. So, this actually is a cross section of that tin lid that we just saw. So, it is a cross section if you take somewhere, and this now can be made into a planar arch. So, here just like the tin lid, if I apply force here, this is one stable state, and if I play this simulation movie, it goes into the other stable state. So, this is the other stable state. By pressing up and down like this, we can switch it between these two stable states. Just like what we did there, when it is in this state, if I were to apply a torque here, then also I can switch it to this other state. So, I do not have to do pushing up here, but instead I can do turning here, just like we did on the red colored tin lid. That is why we call it a tin lid curve. Lot of different arches will give you this bistability. So, now what we want to discuss is whether we can draw these kinetoelastostatic maps for bistable mechanisms or bistable arches, shells, or in general mechanisms, and that is possible as shown here. In this particular case, we are drawing these curves. On the y axis we have the displacement u by L. By u by L, what I mean is this stroke, this displacement from here, how much ever it moves, let us call it u, and this length, there is a characteristic length for the arch, that is L. So, we have on the y axis that u by L, on the x axis we have eta. So, eta, as you recall, is f L square by E b d cube. We also write it as L by d as S, in which case it will become f s square by, this is also written as f s square by E b d. So, d square L square becomes this S, which is slenderness ratio. Whereas, here we have plotted different curves, not for different values of S, but different values of L by H. That is what is shown here. What is H here? H is the height of the arch. So, you have from here to here, there is a height, different curves you take, the height of the arch will vary, that is H. So, it is drawn for different L by H ratios, starting from 2.5 going all the way to 40. So, if you see the first one, this is for 2.5 L by H as indicated there, and then 3, 4, 5, 8 up to 40. We stopped at 40. If you see, this is a bistable curve. Let me take the last one. This is a bistable curve, right. So, the force is in this axis, that is eta axis is force here, and here we have displacement. So, force is 0 here, 0 there and 0 there, that is a bistability. Let me use a different color to show you better. So, force is 0 there, 0 here and 0 there. So, it is bistable, stable here, unstable in the middle point. If I take a bigger curve, let us take the green curve. The green curve goes like this, like that, like that. I have drawn blue color over green. So, again this is one stable point, this is another stable point. In between, let me take unstable to be red, unstable point, right. But as you increase L by H ratio, these points are coming closer to each other. More importantly, this height is reducing, right. So, for 2.5 it was so large and now it becomes small, and if you make this L by H larger, at some point it will not intersect the axis again, it lose bistability. That is what these curves already tell you. For L by H ratio, very large value, it may not even be bistable. And it also tells you how much the travel between the two stables. For example, the blue one, the travel is from there to here, it is like a stroke of the bistable mechanism. That is, the arch when it goes from here to when it goes to the other end, right. So, where we put the arch, so it went all the way up there to where it is, right. This is the travel, and the travel also is visible here, that is this for the blue curve, which is L by H there is equal to 8. So, we can read the travel, we can also look at the switching force, because switching force is given by this eta value, right. Unless you put that force, it will not switch to the other state. So, we have to apply force, increase it up to this value, then it can go with the negative slope here, it will just go to the other state. It gives you the switching force over here. This is switching force for each curve, and also there is switch back. When you want to come from there to here, this will indicate switch back force, switch back force. We have that also here, that is eta value. If you know the rest of them, you can compute. Similarly, you can plot the stress also for these things, and that is what is shown here, sigma star here, non-dimensionalized stress value, and that stress also again eta is in this axis, which includes force. We can see as you increase the force increases and then decreases. That is why these curves are turning back. Again, if I go to this green curve, which is L by H equal to 8, so the stress varies like that. So, we have an indication of what stress is when I go from one state to another state, what happens. Okay, force increases and decreases because it is bistable. In the end, it should become 0 again, right. So, the force should come back to 0 again, and it goes a little farther than that. So, we can see what happens to the stress as well. So, we can calculate the stress from this non-dimensional map for non-dimensionalized stress, and we can also get that stroke or travel and switch back force, switching force, all the important parameters we need can be captured for a number of L by H values. Now, let us see how we can use these when there is moment actuation rather than force. Why moment actuation? Let us go back and look at this. We can either apply force to switch it from state to state, or we can apply torque or moment here. So, torque or moment we can apply and switch it from one state to another state. So, if you want to know how much, that also can be drawn as shown in this non-dimensional plot, where you cannot see here, but this also eta, but this eta is defined now not as FL square by EBD, but as ML by EBD cube. Okay. Previously, it had FL square. To have the M units, moment has Newton meter, it becomes only L. So, we can do this, or if you want to write it with S, it will be MS by EBD square, because d cube 1 d will go for S. So, for different values of eta, again if you draw, you can see the U by L now how it goes, and you can see that this one has already lost by stability, because it is not cutting the 0 moment axis. If it is bistable, moment should become 0 again. So, it is barely, for L by H equal to 20, it is barely bistable. The curve is just grazing the m equal to 0 axis, meaning eta equal to 0 axis. So, this axis again is eta here. Okay. So, we can make out, similarly we can draw the stress plot when you apply the moment load. We can do that for various L by H ratios here, and then see how again what is the switching moment, that will be this value here, and then switch back moment for that L by H equal to 8 over here. Okay. So, we can look at that, and also travel from here to here, how much does it actually move for this other stable state. Okay. So, a lot of information is contained in these non-dimensional maps. And how is it useful? The stress again for the moment actuation, we have eta here, ml by EBD cubed, again this is eta equal to ml by EBD cube, and this is sigma star, non-dimensionalized stress, that is sigma times S divided by E. This is maximum stress into S divided by E. That is how it is plotted. We will know what stress is. So, we can use these maps to do design of these compliant bistable mechanisms or just bistable arches. So, let us take a problem which has this design requirement. L, that is this, should be less than or equal to 30 mm. Somebody had put that, let us say, requirement, and W, which is the out of plane, that is why it is shown with this symbol here. It is the out of plane thickness that is out of the screen, that should be greater than or equal to 13 mm, somebody has said, okay, that should be greater than or equal to that, and then force of switching should not be more than 50 newtons, and let us say that we want to make it with steel, in particular spring steel, because that has very good elastic properties to go back and forth and high strength as well. If we want to design that, how do we get this? So, we first of all we need to know this is a cosine, double cosine arch, it could be Tinley, it could be sine. There are several arches that one can design for this, and for all those arches, if we have this kinetoelastostatic maps, the kinds of 4 maps that I showed just now, one can actually design this without much calculation, as we will see. Okay. So, let us take this particular one with the force actuation, different L by H values, and in particular here let us say we choose the curve L by H equal to 4. Okay. You have to do trial. So, if I take this, let me trace over L by H 4. So, that is this curve. Okay, I am going backwards here. So, this is from state 2 to state 1 in a way, and then goes like this, and here you can see this number eta here corresponds to 22.786 or whatever, does not matter, 779 we can say, okay, how many ever digits you want to take. That is a switchback eta, and L by H equal to 4 we are taking, that is the height is about 20% of the span of the arch. Okay. You can make that choice. In that case, you can get a travel over here. If you see, this is 0.5, okay, this is 0.4, that is u by L, transverse displacement divided by length, and you will get roughly slightly less than half, that is u by L, that is the displacement or a travel or a stroke is half of the size. That is an interesting, if you have this, it will go so much. Okay. So, you have that and you are choosing that based on that L by H equal to 4, for that eta equal to 22.786. Now, if you put that eta equal to 22.786, and then you know that if it is Fs square by EBD, or this is also FL square by EBD cube. Okay. So, now let us go for L equal to what is given there in the design requirements. If you see, we want to have L less than or equal to 30 mm, let us take all of it. When somebody say less than or equal to, the bigger it is with steel, if you think it is better, then let us take it as 30 mm, that means that 0.03 meter square, okay, 30 mm we have, and then force is 50, it should not be more than that, again that is a design requirement. F is 50 newtons, we have taken that 50 newtons here. Steel, so we have taken 210 gigapascal for E, and then we have BD cube, again this is S and we have BD cube, right, we have this. So, from here if I know eta, we have chosen that L by H is equal to 4, that is I have taken an arch. So, I think this arch is I am not indicated which one here, let us assume that it is for a fixed beam with a cosine. So, for such a thing, if it is like this, if this is L and this height is H, okay, fixed cosine, and that needs double cosine arch in order to avoid asymmetric mode, okay, that will be like this double cosine that we saw in the picture. So, that okay, like this, okay, if we have this is the D, okay, this is the H that we see, the cosine, double cosine with the connection in the middle, and D is the depth of this arch beam, and F is the force, U is that stroke, L it is there, W is the out of plane, or it could be also W is equal to B here, that is the dimension in the perpendicular direction to the plane of deformation of the beam. Okay. So, that BD cube now if you work it out, you will get a value like that. Now, if you say B equal to 1 millimeter, that is the thickness of the sheet from which you are going to make the arch. If you take as 1 millimeter, the D will turn out to be 0.21 millimeter. That is, you have to make in plane width of that very small. That means that it is going to be more like a sheet that is bent here like that. So, the in plane one, this dimension is now D equal to 0.21 millimeters, that is 210 microns, whereas this out of plane thing here is our B, or we can also call W, that is 1 millimeter. That is, from a sheet of 1 millimeter thickness, you can cut this arch, maybe wire EDM or a method like that. So, you can make this arch, clamp it at both ends, it would serve the purpose. And you can also look at the stress if you want, and then make sure that it is less than the strength of steel. So, kinetoelastostatic maps help us design things very quickly. It is a very nonlinear one, bistable behavior, because it goes up and comes down and goes up, right. Highly nonlinear behavior. Even then, without even doing a finite element analysis, we can design these things, provided we have these maps that are at our disposal, okay, all the maps that we discussed. So, it is an example to indicate that bistable devices also can be designed using these maps, and in fact, here that particular thing we just designed was put into finite element software console to show that the force here, okay, the switching force is actually 50. If you look closely, this is minus 50 here, this is going down, and it actually comes there with the travel which is indicated over here. We said 13 millimeters, this is 0.013, that is exactly what we have, it comes, because kinetoelastic maps are created using finite element analysis. It is no surprise that we get back what we have. So, those maps contain the information about a lot of finite element analysis, even though to create that map you only need a handful of finite element analysis, as we have discussed. So, for example, to create a map like this, if there are 1, 2, 3, 4, 5, 6, 7, 8 curves to draw, you need only one finite element analysis for each. If you do that, you have this information so that you can design a number of things after that, for stiffness, force deflection behavior, strength, and so forth. So, to summarize, the main points are that kinetoelastic maps can be used to quickly assess if a given compliant mechanism can be scaled up or down, make bigger, smaller, does not matter because it is non-dimensional. And we illustrated that using 3 examples in static applications, including one for the bistable mechanism. That nonlinearity which is inherent there is captured really well here, as we saw in this example, and later on we can extend this to dynamic applications in the next 3 lectures. So, for the reading of this one, there are a couple of papers that I have alluded to, and a thesis, a master thesis of Harish Indukuri, where you can see that this method was developed and described in this master's thesis, and these 2 papers give examples of where we have used this in our research. Thank you.